Look how the person's now.
1%. Okay. Thanks.
Oh, Brian, we got a question. Oh, okay, why don't you just ask me? Okay. Okay. So, continuing, okay, so that's the end of our exam. So now we're going back to basically the formalism of chapter 7 and the grand canonical formalism. And let me show you something, let me first remind you of something we studied in the canonical formalism, and then show you how we can extend it in the grand canonical formalism. Remember back in the canonical case, our system is exchanging energy, only energy, with the reservoir. And you can use the partition function, regular partition function, to find the thermal average energy, E bar. And then you can even find the standard deviation of the energy, which is going to be a measure of how big the fluctuations of the energy are away from the average. Sigma sub E as the square root of E squared bar minus E bar squared. This should be ringing a bell a little bit. And you can calculate the size of the energy fluctuations by taking the standard deviation of the energy, sigma sub E, and dividing it by the average energy, E bar. And you find that the size of the energy fluctuations go like 1 over the square root of n, where n is the total number of particles in your container. And that's a big. So 1 over the square root of big is small. So the relative size of the energy fluctuations, small. You can do the same thing in the grand canonical case, because the system can exchange energy with its reservoir. So you can ask for the relative size of the energy fluctuations. And you would get getting basically the same result. That's not so interesting. We won't do that again. But what is new now is you can also say, but wait, the system can also exchange particles with the reservoir. So now I can ask, since over time the number of particles could be changing, what's n average? What's the average number of particles? Thermal average. And then eventually I can ask how big are the particle number fluctuations. In other words, it's the same kind of thinking we did with energy, but now it's with particles. Okay? Okay, so moving on, I'll come up now to part C. Grand partition function and particle number. So we know in this approach that we have a system that is in thermal and diffusive equilibrium with a reservoir. And we can ask about thermal average values of things like the average number of particles in the system, which we will denote capital N bar. Okay? The starting point will be, the safest starting point is to base this calculation purely on fundamental meaning of average. Namely, I'm going to sum over all the states that are available to the system. I'm going to take the number of particles for that state S times the probability of that state S. This is how you find the thermal average value for any quantity, yes? Any generic quantity whatsoever. Q bar is the sum over S, the value of Q in state S times the probability of state S. What you have to, of course, remember is that in the grand canonical approach, you must use the correct probability function, which in the grand canonical approach means take the Gibbs factor divided by the grand partition function. So that means take the sum over S, the number of particles for state S, times the Gibbs factor, e to the minus beta times energy of state S minus chemical potential times particle number for state S, all over the grand partition function. And of course, the next thing everybody does is bring the factor of 1 over the grand partition function out front of the sum. Sum over states S, n of S, e to the minus beta times e of S minus mu n of S, like that. Be careful with this, by the way. You cannot, by the way, take this factor here of the exponential, look at that sum over S and say that's the grand partition function and cancel that z. Because it's multiplied by this other quantity that depends on S inside this sum. Okay? So you can take it no further in terms of simplifying than that expression right there. Okay? I can, however, observe another way mathematically to express this sum. So now we're going to start making a number of observations, all based on wonderful properties of the exponential function. For example, I could just observe that if I take the partial derivative of the grand partition function with respect to the chemical potential mu, I can do that derivative if I wish. That will give me, remember, the grand partition function is the sum over the states of the Gibbs factor for each state. So the grand partition function, script z, is the sum over S without this, the Gibbs factor. So when I differentiate with respect to mu, there's the factor of mu. So I'll just get the exponential, and then I'll differentiate with respect to mu, so I'll have a factor of beta and n of S. Okay? So this partial is the sum over the states, factor downstairs of beta n of S times the Gibbs factor. Okay? That is merely an observation of what you get if you take the partial derivative of the grand partition function with respect to the chemical potential. But now compare that, there's a reason that's a helpful observation. Compare that with our expression for n average. Okay? The key part is the sum over S, n of S times Gibbs factor. The beta, that can come out front. Okay? But sum over S, n of S Gibbs factor, that's a key part of n bar over here. Sum over S, n of S Gibbs factor. All I'm missing there, in order to have n bar, is a factor of z downstairs, and I have an extra beta. Okay? So just by comparing, I see that I can express n average as 1 over beta times z times the partial of z with respect to mu. Now I'm back to numbering my equations the way I have been in this section. So this is equation 4, right? This equation, it's not because this was a 3, this was within the example, that's separate. Right? It's because the main part of our notes, the last equation was a 3. Okay? So you can get n average from the partition function, grand partition function, by taking the partial with respect to mu. Just like you would get E average by taking the partial with respect to beta. Okay? But we're interested in what's new in this formalism, and n bars. Well, I'm heading towards also getting the standard deviation in the particle number. How much is it fluctuating away from the average? So another thing I'm going to need, I'm going to want to know what is the average value of the particle number squared. Well, I know how to set up any kind of average value that you want to know. Right? Sum over the states the value that you want to know, evaluated for that state, so I'll have a sum over S, n squared for state S, times the Gibbs factor for state S, and divide by the grand partition function. Which we might as well write like this. N squared average is 1 over the grand partition function, sum over the states, n squared for state S, times the Gibbs factor for state S. Okay? Now let's make another observation. Let's take two partials of the grand partition function with respect to mu. Oh, why not? Okay? Notice when we did one partial of the grand partition function with respect to the chemical potential, we brought down a factor of beta times the particle number for state S. And then we still had the Gibbs factor. So when we do another partial, right, well, we're just going to bring down another factor of beta times n of S. So two partials of Z with respect to mu is sum over states S of beta squared n squared of S times the Gibbs factor for state S. Okay? You can see perhaps where this is headed. Notice then, I've got the key part here on the left of what I have right above for n squared average. I've got a sum over S of n squared of S times Gibbs factor, like I have here. What I'm missing here is a factor of 1 over script Z, and I have an extra beta squared. So, by comparison, I see that n squared average is 1 over beta squared times script Z times the second partial of script Z with respect to mu. Let's number that one. That's equation 5. So now n squared average is connected to the partition function. Now let's find the standard deviation of the particle number. How much variation is there? Sigma sub n. That's the square root of n squared average minus n average squared. Be very careful with that notation. Square root of n squared average minus n average squared. And use equations 4 and 5. Okay? For n squared average here, use equation 5. For n average, use equation 4, but note that you'll have to take that expression for equation 4 and square it. So when you do that, you will have, inside square root, 1 over beta squared, 1 over script Z, 2 partials of script Z with respect to mu, so that comes from equation 5, minus equation 4 squared. 1 over beta squared script Z squared. 1 partial of Z with respect to mu squared. Look very carefully at that notation. Okay? Equation 5 minus equation 4 squared. Again, note very carefully. That and that are not the same thing. Now, I can factor some stuff. At least I can factor the 1 over beta squared out front, so I'm not going to worry too much about that. Okay? But it looks pretty messy. So another helpful observation would be nice. So here comes another one. What do we get if we take It's a little bit different. The partial with respect to mu of n bar. Okay. Here's how you get n bar, equation 4. But when all is said and done, and you've done this calculation to get the expression for n bar, it's going to depend on mu. So you can ask, what do I get when I do that derivative? Okay? All right. Well, let's use equation 4. So I'll put a question mark there, and then I'll say use equation 4 for the expression of n bar. Take the partial with respect to mu. Where is the mu dependence in equation 4? It's in z. Right? So here and here. So I have to do the product rule. Okay? So here we go. Partial of n bar with respect to mu, using equation 4 and using the product rule. We got that term right there first. So that'll be minus 1 over beta times script z squared downstairs times the partial of script z with respect to mu. That's just from this term right here. Differentiating it with respect to mu and the fact that it's in the denominator. Okay? And then they're still multiplying that factor, partial of z with respect to mu. So there's the first part of that derivative. Okay? Right there, comes from that term. Then, plus 1 over beta script z times the partial of this with respect to mu. Well, it's already one partial, so now it becomes a second partial of z with respect to mu. See, I just did the product rule. Okay? I mean, if you want to think of it as the quotient rule, you can, but the quotient rule is the product rule. Okay? Note I'm going to write this now like this. 1 over beta z times the second partial of z with respect to mu minus 1 over beta z squared times the first partial of z with respect to mu quantity squared. Now look at the expression for sigma sub n. Okay? So compare the expression we got for that derivative, partial of n bar with respect to mu, with the expression for the standard deviation in n, sigma sub n. The key things are there. 1 over z, second partial of z with respect to mu. 1 over z, second partial of z with respect to mu. Minus. 1 over z squared, partial of z with respect to mu, quantity squared. 1 over z squared, partial of z with respect to mu, quantity squared. Okay? So, what I contend is that I could just, this beta squared stuff, go out front, right? And that beta there is also common to those two terms. So here's what I claim. Sigma sub n is 1 over beta square root of beta times partial of n bar with respect to mu. So you can simplify that then. Square root of 1 over beta partial of n bar with respect to mu. Okay. And of course 1 over beta is kBt, so sometimes you'll see it written like this. kBt times the partial of n bar with respect to mu. That's equation 6, because that's a pretty compact way to calculate the standard deviation in the particle number. Now if you go back into chapter 6 with the canonical formalism, where the only thing exchanged with the reservoir was energy. We went through a similar kind of derivation for energy. Okay? And you could end up expressing the standard deviation in the energy as a square root of the average energy with respect to temperature. It's a very similar expression for sigma sub E in the canonical formalism. Okay? So what you want to do is you want to convince yourself that just like we did in the canonical approach, that energy fluctuations are small for any kind of real-sized system. Let's see if they're small. Particle fluctuations are small. Okay? Now what I'll do is I'll do a simple little application of this. It's not a thorough derivation. It's just a simple little hand-wavy calculation. What I'm going to do is I'm going to look at the monatomic ideal gas our old friend, where we know that we can get an expression for the chemical potential, mu. I'll remind you, we talked about it in the example, I think, the first part of class today. Negative kBT, natural log of volume of container over number of particles times the quantum volume. Now what I'm going to do is I'm going to say, let me make an assumption and then see if I get a contradiction to that. Let me assume that the particle number fluctuation is going to be small about the average value of n. So in this equation, I'm going to replace this n with n bar. If the fluctuations in particle number about the average are small, then that's a reasonable substitution to make. That the number of particles is just going to pretty much always be the average value. So if that's true, I'm going to put an n bar there, and then I'm just going to solve that expression for n bar.
Sorry, can you repeat again the area of why are we trying to substitute the n bar?
Because we're just assuming the fluctuations are small, right?
Right.
If fluctuations are small, then the particle number is pretty much always the average value. Just like we saw with energy. Okay? So we're going to solve this equation for n bar. You can do that. I'll just write down what you get. N bar equals volume of box over quantum volume times e to the mu over kBt. So I solve for n bar as a function of mu. You see why I wanted that? So that I can apply equation 6. Equation 6 says to get the standard deviation of the particle number, take the partial of n bar with respect to mu. So I needed to know n bar is a function of mu. Okay? So now I can calculate, that is to say, write down a symbolic expression for the partial of n bar with respect to mu. Nothing here depends on mu except right there. So that'll just stick around. I'll have an e to that same blob, and when I differentiate this blob with respect to mu, I'll get a 1 over kBt. Okay? So this will be 1 over kBt times capital V to the quantum volume, e to the mu over kBt, right, from the derivative. But wait, what's this part right here? Right here. It's n bar, yes? So this derivative is n bar over kBt. Yes? Okay? All right. Now, use equation 6. Use equation 6. So, sigma sub n, the standard deviation in the particle number, is the square root of kBt times the partial of n bar with respect to mu. That's n bar over kBt. So that's just the square root of n bar. There's another square root of n, basically. Yes? So then, what's the relative size of the fluctuations that you might observe in the particle number for this system, for the monatomic ideal gas? That means take sigma sub n and divide by n bar. How big are the fluctuations relative to the average value? All right? Well, that's square root of n bar over n bar, so there's your 1 over the square root of n bar. But that's going to be much, much less than 1 for any kind of monatomic ideal gas where n bar is of the order of 10 to the 23. So for any kind of standard size system, the fluctuations in particle number away from the average value are minuscule. Just like the fluctuations in energy away from the average value for the energy are minuscule. Okay, so there's another bit of practice with the grand canonical formalism. You can ask for the value of n bar. And then once you get n bar, you can pretty much say, that's how many particles my system has. Okay, now, let me take a few minutes and start us transitioning to get to the point where we can get the last big idea in chapter 7. It's still going to be about applying the Gibbs or the grand canonical formalism. Okay? But now this is a new section here. We're going to talk about what I'm going to describe as dense systems and quantum statistics. I have to explain what we mean by these things. Let me start with a reminder of what I had about a week ago, where I talked a little bit about the so-called quasi-classical analysis of a system. So let me remind you, what is the condition for using a quasi-classical analysis? The condition is that the thermal de Broglie wavelength, also known as the quantum length, must be much smaller than, notice this number, the volume of the container over the number of atoms to the 1/3 power. That is the inter-particle separation. How far apart the particles are is large compared to how large the wave function is for the particles. And the kind of picture I drew for this kind of scenario was if I represent each particle as a little furry probability cloud, that's its wave function, right? Then the diameter, in essence, of that probability cloud, the wave function, that's the thermal de Broglie wavelength, also called the quantum length. And of course, each one of these has some velocity at any given time. Over here might be another probability cloud for another particle. Okay. Again, its diameter will be of the order of the thermal de Broglie wavelength, and it can be moving at a certain velocity at a given time. And then the distance between them is the interparticle separation. And if the quantum wave functions, the probability clouds, their extent in space is small compared to how far apart these two are, right? That's not a dense system. That's a dilute system. Okay? And you can use what's called a quasi-classical analysis. And that's pretty much, that is the analysis of chapter 6. Okay? So when I say quasi-classical analysis, I mean chapter 6. Now notice another way to write this condition, that the thermal de Broglie wavelength, or the quantum length, is small compared to inner particle spacing, is to just cube both sides of that. So another way to write that condition is to cube both sides. L cubed must be much, much less than the total volume of the container divided by the number of particles. But L cubed is what we call the quantum volume. So the quantum volume must be much, much less than the volume per particle. Let me remind you one more time, the expression for the quantum volume, it's Planck's constant. There's a number of ways to write it. I'll write it this way. 2 pi mass of particle kBt, that's in square root, and the whole thing is cubed. I mean, that's one way to write it. So I'm needing that to be much, much less than the total volume divided by the total number of particles. Notice that you can think of this quantity here as the inverse of the particle density. Okay, this is our first equation for this new section, equation 1. With that being satisfied, you can use the canonical formalism. Okay? And so you use the canonical formalism which I remind you means you have a partition function, Roman z, okay? This is an n particle partition function. And it can be written in a number of ways depending upon what's happening. If you have distinguishable non-interacting particles, you can tell them apart and they're not interacting. To get the n particle partition function, you just calculate the partition function for every one of the n particles separately and then multiply them together. Or, if you have indistinguishable non-interacting particles, then all you got to do is find the partition function for any one of them, z1, raise it to the n power, but then, because it overcounts, you have to divide by n factorial. Because it overcounts the states when you raise z1 to the n. We talked about that. Chapter 6. Okay? Okay, that's by way of review. Because now we're going to go and do something in distinction to this, that's different from this. That's where we're headed. Okay? Namely, what if you have a scenario where this equation or condition labeled equation 1 isn't true? How do you deal with it? That's now where we're headed. Okay? So, first let's think about how you might end up in a situation where that inequality in equation 1 is violated. Okay? So B, let's just ask ourselves, what could cause equation 1 to be violated? In other words, just the same question reworded, or what could cause the quantum volume to be larger than or of the order of the volume per particle? And I'm not asking anything too tricky here. I just want to look at the expression for the quantum volume and the other side of equation 1, the inverse of the particle density, and think about how I could end up getting a situation where this is comparable to this, or maybe even bigger than this. Okay? Here are some ways that might happen. Okay? I'm just giving you a list of how this might happen. Okay? One way is to have particles with a very small m. Yeah? Right? Very small mass particles are going to make the quantum volume pretty big. In fact, I made a table last week where I looked at a gas of free electrons, such as you might find in a metal. Okay? And I discovered that this is violated. So that if you want to understand the conduction electrons in a metal, you can't do chapter 6. Okay? So a small m could get you to this situation. What are other ways? How about a low temperature? A low enough temperature can get this pretty big and get you to that you're in this situation. Okay? Another way it might happen is high particle density, N over V. Particles per unit volume. Because that would then make this small. Okay? So there's more than one way that you can end up in this boat. Okay? The new picture, by the way, the new schematic picture of what's physically going on is quite different from that. Because now you have particles with probability clouds that are bigger. Okay? The diameter, the order of the de Broglie wavelength, or the quantum length. Moving around. But then the next probability cloud's right there. Okay? Moving around. Okay? With its size, lambda thermal. And the distance between them, V over n to the 1/3, is not large compared to the quantum length. And you could draw more of those clouds, but the point is they're right up against each other. Overlapping even. Okay? Overlapping even. So how do you deal with this scenario? That's what we're talking about for the rest of this chapter. It's going to boil down to one more key idea. In order to deal with this, what I call high density situation, you have to also worry about the two species of indistinguishable particles that exist in nature. Species, quote. Two species of indistinguishable particles in nature. Okay? And this is where the phrase quantum statistics comes in. Because when you are doing quantum statistics, you are worrying about which of the two kinds of species of particles you're dealing with. Okay? So these species are given names. They're named after people who did some of the first work in quantum statistical mechanics. And so one species, a particle, is called a fermion, named after Fermi. Okay? A fermion is any particle with an odd half-integer quantum number. So little s, the spin quantum number, is an odd half-integer. So 1/2, 3/2, 5/2, dot, dot, dot. Okay? That's a fermion. Any particle whose spin quantum number is an odd half-integer. Of course, there are a number of examples. Electron, proton, neutron are the three most famous fermions. Okay? What is the hallmark of a fermion? The hallmark of a fermion is that when you write down the wave function describing a system of two or more identical fermions, the wave function must be anti-symmetric with respect to particle number, particle label exchange. If you exchange the labels, like you give labels 1 and 2, and you exchange those labels, the wave function has to pick up a negative sign. That sounds pretty abstract, but the consequence of that fact is that no two particles can be in the exact same state at the exact same time. And we know what that's called. That's called the Pauli exclusion principle. Okay? So, no two identical fermions can occupy the same single particle state. That's a fancy way, by the way, single particle state, for saying have the same set of quantum numbers. Okay? Have same set of quantum numbers at the same time. That property comes from that asymmetry in the wave function that I mentioned when you exchange the labels on the fermions. Okay? So, as you know, this is called the Pauli exclusion principle. That's one kind of species of particle in nature, a fermion. Okay? And in three-dimensional space or higher, there's one more type of particle you might come across, what's called a boson. And that's a particle whose spin quantum number, S, is an integer. So 0, 1, 2, dot, dot, dot. So an example that condensed matter physicists like to trot out as an example of a boson is a helium-4 atom. Because it has 2 protons, 2 neutrons, 2 electrons. An even number of fermions, each with their own spin quantum number of 1/2, you end up with a total spin quantum number of 0. Which puts it in the boson category. Okay? Now, how do bosons behave? Well, their wave function for 2 or more identical bosons must be unchanged when you switch the particle labels. No minus sign pickup like you do with fermions, but unchanged. Okay? That turns out to have the consequence that bosons don't satisfy the Pauli exclusion principle. You can have 2 or more bosons in the same single particle state at the same time. Okay? So here we say any number of identical bosons can occupy the same single particle state at the same time. There is no exclusion principle for bosons. Okay? In fact, if the temperature gets low enough, bosons like to all go into the same state, the lowest energy one. That's called Bose-Einstein condensation when that happens. So these are kind of like the opposite ends of, to use kind of an anthropomorphic example, these are the quintessential party particles. They want to be together in the same state, temperature's low enough, and these are the quintessential antisocial particles. They don't want to be in another state with another fermion. Okay? Alright, so we're going to have to deal with, are we working with fermions or bosons? Okay, so that's where we will pick up on Thursday.